In most areas, it is now a requirement to install separate grounding conductors in all conduits, including rigid metal pipe, intermediate metal conduit, electrical metallic tubing, and polyvinyl chloride conduit. This requirement is outlined in the National Electrical Code, specifically Article 250.118. Metal sheath cables, such as armored cable and metal clad cable, do require bonding bushings with attached lugs to connect and bond the sheath of the cable with the rest of the installation. National Electrical Code Article 250.118(7) requires this bonding at both ends of the cable run. The traditional practice of using the metal conduit as the grounding conductor is still acceptable in some situations. However, the current trend is to install separate grounding conductors in addition to the conduit, providing a redundant path for fault currents. Grounding serves several purposes, including protection against electric shock by providing a low-resistance path for fault currents to flow from the equipment to the earth, preventing dangerous voltages from building up on the enclosure, protecting equipment by providing a path for lightning surges and other transient currents to dissipate harmlessly, and ensuring proper operation of protective devices, such as fuses and circuit breakers, by providing a reference point for fault currents to flow to. The National Electrical Code requires grounding conductors to be sized based on the circuit conductors they protect. The minimum size for a grounding conductor is American wire gauge number 14 copper or American wire gauge number 12 aluminum. However, larger grounding conductors may be required for fault currents exceeding 1000 ohms. If a person comes into contact with a grounding wire during a fault, the severity of the shock will depend on the magnitude and duration of the fault current. Even relatively small fault currents can cause significant burns or electrocution. To minimize the risk of electrical shock, it is crucial to ensure that grounding systems are properly installed and maintained. This includes using correctly sized grounding conductors, bonding all metal components, and providing ground fault protection devices where necessary. Grounding conductors play a crucial role in electrical safety and system performance. Firstly, they provide a low impedance path for fault currents, which helps to quickly trip over current protection devices like circuit breakers or fuses, minimizing the duration of a fault and reducing the risk of electrical shock or fire. Secondly, grounding helps to stabilize voltage levels, preventing equipment damage and ensuring proper operation of sensitive electronic devices. Thirdly, a well-designed grounding system can mitigate the effects of electromagnetic interference, improving the reliability and performance of electronic systems. The size of the grounding conductor is determined by the size of the circuit conductors it protects, as specified in the National Electrical Code Table 250.122. The larger the circuit conductors, the larger the grounding conductor must be to safely carry fault currents. Common grounding conductor materials include copper and aluminum, with copper being the preferred choice due to its lower resistance and higher conductivity. Aluminum conductors must be sized larger than copper conductors to provide equivalent performance. Grounding electrodes, such as ground rods, ground plates, or underground metal water pipes, are used to connect the grounding system to the earth. The National Electrical Code requires that grounding electrodes have a resistance to ground of 25 ohms or less. If the resistance is higher than 25 ohms, an additional grounding electrode must be installed. Bonding is the process of connecting all metal parts of an electrical system together to create a continuous low-impedance path to ground. This includes metal conduits, metal enclosures, metal equipment frames, and metal water pipes. Bonding helps to prevent voltage differences between metal parts, reducing the risk of electrical shock. Bonding jumpers are used to connect metal parts together, and they must be sized according to the National Electrical Code Table 250.102. Ground fault circuit interrupters, GFCIs, are devices that detect ground faults and quickly interrupt the circuit, protecting people from electrical shock. The National Electrical Code requires GFCI protection in certain locations such as bathrooms, kitchens, and outdoor areas. Surge protective devices, SPDs, are used to protect electrical equipment from voltage surges caused by lightning or other transient events. SPD divert surge current to ground, preventing damage to sensitive electronic devices. Regular inspection and testing of grounding systems are essential to ensure their effectiveness. This includes visual inspection of grounding conductors and connections, as well as testing of grounding electrode resistance. Any damaged or corroded grounding component should be replaced immediately. The National Electrical Code provides detailed requirements for grounding and bonding of electrical systems. It is essential to consult the National Electrical Code and follow its guidelines to ensure a safe and reliable electrical installation. Grounding and bonding are critical aspects of electrical safety, and proper installation and maintenance of grounding systems are essential to protect people and equipment from electrical hazards. Factors influencing grounding system design include soil resistivity, fault current levels, and the sensitivity of electronic equipment. Soil resistivity varies depending on the type of soil, moisture content, and temperature. High soil resistivity can increase the resistance of the grounding electrode, reducing its effectiveness. Fault current levels depend on the size of the electrical system and the available fault current from the utility. Higher fault current levels require larger grounding conductors and more robust grounding electrodes. Sensitive electronic equipment, such as computers and medical devices, may require dedicated grounding systems to minimize noise and interference. Grounding systems can be classified into several types, including single-point grounding, multi-point grounding, and hybrid grounding. Single-point grounding is used to minimize ground loops in sensitive electronic systems. Multi-point grounding is used in large electrical systems to provide multiple paths to ground. Hybrid grounding combines the features of single-point and multi-point grounding to optimize performance. Grounding system design should consider the potential for corrosion of grounding conductors and electrodes. Corrosion can increase the resistance of the grounding system and reduce its effectiveness. Corrosion-resistant materials, such as copper-clad steel or stainless steel, should be used in corrosive environments. The use of exothermic welding is recommended for making grounding connections. Exothermic welding creates a permanent, low-resistance connection that is highly resistant to corrosion. Grounding system documentation should include a detailed grounding plan, showing the location of all grounding conductors, electrodes, and bonding connections. The grounding plan should be kept up to date and readily available for inspection. Grounding system training is essential for electricians and other personnel who work on electrical systems. Training should cover the principles of grounding, the requirements of the National Electrical Code, and the proper installation and maintenance of grounding systems. Proper grounding and bonding are essential for ensuring the safety and reliability of electrical systems. By following the requirements of the National Electrical Code and implementing best practices for grounding system design, installation, and maintenance, it is possible to minimize the risk of electrical shock, fire, and equipment damage. Moreover, grounding practices can vary based on the type of electrical system, such as residential, commercial, or industrial. Residential grounding typically involves grounding the service neutral conductor to a grounding electrode system consisting of ground rods or metal water pipes. Commercial grounding systems often include supplemental grounding electrodes and bonding of metal raceways and enclosures. Industrial grounding systems may require more extensive grounding networks to handle higher fault current levels and protect sensitive equipment. Special grounding considerations are necessary for systems with sensitive electronic equipment. Isolated ground receptacles and dedicated grounding conductors can help to minimize noise and interference. Shielded cables and filters can also be used to reduce electromagnetic interference. In addition to grounding for safety purposes, grounding is also important for lightning protection. Lightning protection systems include air terminals, down conductors, and grounding electrodes. The purpose of a lightning protection system is to provide a path for lightning current to flow to ground without causing damage to the structure or its contents. Regular inspection and maintenance of lightning protection systems are essential to ensure their effectiveness. This includes checking for corrosion, damage, and loose connections. The National Fire Protection Association Standard 780 provides requirements for the installation of lightning protection systems. Effective grounding and bonding are crucial components of a comprehensive electrical safety program. By implementing best practices for grounding system design, installation, maintenance, and inspection, electrical professionals can help to protect people and property from electrical hazards. It is also important to stay up to date with the latest codes and standards related to grounding and bonding. The National Electrical Code is updated every 3 years, and it is essential to be aware of any changes that may affect grounding practices. Grounding systems should be designed and installed by qualified electrical professionals who have the knowledge and experience to ensure that the system meets all applicable requirements. It is also important to use high-quality grounding products that are listed and labeled by a recognized testing laboratory. The selection of grounding electrodes should be based on soil conditions and local code requirements. Common grounding electrode materials include copper, copper-clad steel, and galvanized steel. The size and type of grounding electrode should be selected to provide a low-resistance path to ground. Grounding connections should be made using approved methods and materials. Common grounding connection methods include exothermic welding, compression connectors, and mechanical connectors. Grounding connections should be protected from corrosion and mechanical damage. The installation of grounding conductors should be done in a neat and workmanlike manner. Grounding conductors should be supported and protected from physical damage. Grounding conductors should be identified by green insulation or green tape. The testing of grounding systems should be performed using calibrated test equipment. Grounding resistance should be measured using a 3-point fall of potential test. Grounding impedance should be measured using an impedance meter. Grounding test results should be documented and retained for future reference. The maintenance of grounding systems should include regular inspection and testing. Grounding connections should be inspected for corrosion and tightness. Grounding electrodes should be tested for resistance to ground. Grounding conductors should be inspected for damage and proper support. Grounding system problems should be corrected promptly by qualified electrical professionals. It's important to differentiate between grounding and bonding. Grounding connects the electrical system to the earth, while bonding connects metal parts of the electrical system together. Both grounding and bonding are essential for electrical safety. Grounding provides a path for fault currents to flow to ground, while bonding ensures that all metal parts are at the same potential, reducing the risk of electrical shock. The impedance of the grounding path is also crucial. Low impedance grounding paths are essential for effective fault current clearing. High impedance grounding paths can limit fault current, but they may not provide adequate protection against electrical shock. The design of grounding systems should consider the potential for harmonic currents. Harmonic currents can cause overheating and damage to grounding conductors and equipment. Grounding systems should be designed to minimize the effects of harmonic currents. The use of surge arresters can help to protect electrical equipment from voltage surges. Surge arresters divert surge current to ground, preventing damage to sensitive electronic devices. The selection of surge arresters should be based on the voltage and current levels of the electrical system. The installation of surge arresters should be done in accordance with the manufacturer's instructions and applicable codes. The maintenance of surge arresters should include regular inspection and testing. Surge arresters should be replaced if they have been damaged or have reached the end of their service life. The grounding of communication systems is also important. Communication systems should be grounded to protect against lightning surges and other transient events. The grounding of communication systems should be done in accordance with applicable codes and standards. The use of fiber optic cables can help to isolate communication systems from electrical noise and interference. The grounding of data centers is critical for the reliable operation of computer equipment. Data centers should have dedicated grounding systems to minimize noise and interference. The grounding of data centers should be done in accordance with applicable codes and standards. The use of uninterruptible power supplies can help to protect computer equipment from power outages and voltage fluctuations.